And it's my pleasure to give a talk here. Okay, let me give my notes. All right. So, good. Well, so what I'm going to talk about is a joint work with Wishgotts and Sunny. Well, let me first explain the motivation that lead us to study this problem. Well, first I want to state it in a very vague way. In certain cases, the basic locus in the fiber at P of a Shimura variety admits a nice description. Okay, so well, I'm going to first explain a little bit about what do I mean the nice description and why we actually care about this. And then, I mean, the goal of my talk today is to make this more precise. I would like to say that recently there actually many research on this kind of phenomenon. I think probably this actually first started with Follett-Wedholm. So they study about the GU1N P inert. So this is the unramified unitary group with a hyperspecial level structure. And then later, by Rappaport Testig Wilson, we studied about the GU1N P ramified. And I have to say some maximum parahoric level. In some cases, they study about the special parahoric. In some cases, not, for some strange reasons. And then later on, the Howard Papas. So they studied the GU22 and also SO2N with a hyperspecial level structure. Well, what does this nice description looks like? Maybe I just give you some examples for the case Rappaport Testig Wilson considered. So this is actually for the P ramified. And let's see. First place I just put the P equal to 3. I definitely want to avoid the P equal to 2. Well, and I want to put this n to be small, 1, 2, and the GU13. Well, the reason that I want to put these two cases because essentially these are actually very different. So if you think about the Iwahawi-Weyl group of these two, one is of the type B, one is the type C. And you can say, so how the basic locus looks like? Well, in the first case, and so this is 1, 2, 3, 4. And in this case, 1, 2, 3. Well, so here each irreducible component is the projective line P1. And if you look at each projective line, each P1 is actually the 4 special point, 1, 2, 3, 4, 1, 2, 3, 4. Each P1 has the 4 special point.
Each irreducible component is 2-dimensional, 3-dimensional.
1-dimensional.
This is the basic locus.
Basic locus. Basic locus is 1-dimensional. And if you look at, OK, so each P1 has 4 special points. They are the same for these 2 cases. But now if you look at the special point, now so here each special point is the intersection of the 2 P1 in this case. And here in this case, each special point is the intersection of exactly 1, 2, 3, 4, 4 of the P1s. OK, so GU12, each special point is the intersection of 2 P1s. And then GU13, each special point is the intersection of 4 of the P1s. And in fact, a better way to explain this is to use varieties buildings. And OK, now let me make this part a bit more precise. Description as a union of, you can say, P1, or in some other cases, it could be the Green-field curve, or in the Howard Papas, this could be the Fermat hypersurface and central. In fact, these are the special examples of the classical Deligne-Lussig varieties. And this union is indexed by the data from the varieties building. So in fact, from the theory of the varieties buildings, one can actually tell that how this irreducible component intersects and how many of them which actually corresponds to each dimension. Well, so this is actually a nice description, but why we actually care about this? This certainly do not always happen. For example, for the Ziegel case, this only happens for SP4. When starting from the SP6, then it becomes more complicated than the classical Deligne-Lussig varieties. Well, the reason is that this explicit description so this, in fact, these are useful. people actually found the application already in various situations. For example, to compute the intersection number. Numbers of the special cycles. And for example, we can study about the Kudala-Rappaport program. And also, this has also been used in the Wei-Zhang's arithmetic fundamental lemma. And another application is to construct the special cycles in order to verify the Tate conjecture in certain cases. So this, for example, this is the work of the Helm, Tian, Xiao, and Zhu. Okay, any questions so far? Okay, now, so in the 45 minutes, what I'm going to do is that I'm going to explain this. What can we see about more explicitly of these certain cases? Let me make this more precise. Before that, there's one case that I would like to mention. This is actually by Harris and Tyler. So this is a GU1N P-split. Well, in this case, it is just a zero-dimensional. Which means just the unions of the points. And the point is a special case of the derivative variety. Excuse me? OK. So this we can consider this as a trivial case for this question. But we're going to see later on that this is actually also probably the most important case. In the end, we're going to see how this special case plays an important role to actually to understand all these situations. OK, so what I'm going to do today is that I'm trying to address the following questions. When, why, and what else? OK, so when does this happen? When does it happen? And so I'm going to give the classifications for those certain cases. And I'm going to explain why does it happen in these cases. And also want to say what are the other nice properties. OK. Well, so here we want to start with special fibers of an arbitrary Shimura variety. So when we talk about the special fiber, we first have to assume that there exists a nice integral models. So then we can do this mod P. OK, so the general setup. So let's see, we start with the Shimura data. And I denote this. This is just a special fiber of the reduction mod P of the Shimura variety. And so what is K? So here K is a parahoric. So subgroup. In all these previous cases, so people actually think about, well, except the Harris-Tyler, people think about the hyperspatial or some maximal spatial parahoric. But here we want to consider about arbitrary parahoric. And so, so first, in order to define this basic locus and also some other stratifications that we're going to use the setup in the joint work with Rappaport. What we consider is the following. So we put up the 5 axioms, 1 to 5. So this allows us to relate the spatial fiber of the Shimura variety with the group-theoretic setting. So I'll first write this down. I'm going to explain in more details. So lambda k and delta k. OK, so here first, we start with the periodic field, but then we consider the maximum unramified extension, and then we do the completion. So we have this is the sigma. So this is the Frobenius. And so here we have the parahoric subgroup inside here. And then this actually leads to the parahoric subgroup of this larger group. And here, this one. So this is contained in the product of this parahoric subgroup. So this is the graph of this Frobenius. So here, if you look at this group, then we have the first k axis on the left, second k axis on the right. And here, this is subgroup. We think about this quotient. And of course, this actually factors through the action of the k times k. Where on the other hand, this is also contained in this. So the B of G, so this is just a set of the Frobenius twisted conjugacy classes of this group. So in fact, these two maps, this has been used quite a lot in the studies of the various stratifications of the Shimura varieties. So let's first look at this map. OK, so what is this one? So this one is in a natural bijection with a double coset of the Xuhua He wire group. So here this W tilde is a Xuhua He wire group of this G and WK. So this is just a wire group of this paraholic. Well, in the case that if the G is unramified and K is hyperspatial, then what you get is just a set of all the dominant weights. Well, but the map from the Shimura variety to this is never surjective. Because here we only use this G, and you now have to take into account of this edge. So this edge will lead to this mu. So this is a co-character of this G. Now, to describe the image, we need the so-called admissible set. So this is by definition just the elements in this Xuhua He wire group that it is less than or equal to some conjugations of this mu for some x. And then we just map to its image in this double coset. And then by the work of the Zhu and Papa's Zhu on the local model, we know that the natural range of this map of this lambda k is this admissible set. And well, what are the fibers of this map? So the fibers of this map, so this is a so-called the Cartwright-Rappaport stratification. Rappaport strata. And now let's look at this map. So what actually is this map? So the B of G. So B of G, so this is actually the sigma isocrystals. So this one is actually classified by Cartwright. In the 80s and 90s. So any sigma conjugacy class is determined by the two invariants. So this is, let's say, each sigma conjugacy class is determined by the two invariants. From the Cartwright map, kappa, and Newton map. And again, this map is never surjective. We also need to take into account of this mu. So this is sometimes called the set of neutrally acceptable elements. So what does this mean? This means that we think about the conjugacy classes inside here and satisfy the two conditions. First is that the continuous map coincide. And second, so the Newton map gives you some rational dominant co-weight. So we want to have that the Newton map is less than or equal to, so this one is the Galois averaging of this mu. So this is also sometimes called the major inequality. And yes.
Can you give some examples of this admissible locus? If K
Okay.
is hyperspecial, is it one element or?
Well, this actually depends. So if the G is unramified, then it is one element. But if it is ramified, it could be more than one element. But I think maybe let me try to draw a picture of this admissible set.
Okay.
Okay, let's see, and if I still remember. And examples. Let's see, admissible set mu for SP4. So this is in the Ziegler case. So we first think about the affine wire group using these R curves. So this one is a fundamental R curve. And I think to draw like this. And so this one is the admissible set for the Ziegler case for SP4. It contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 elements. It is.
So when you say the Siegel, you mean the Siegel parahoric?
No, I mean I take the parahoric to be the Iwahari.
Oh, for the Uhoric.
Yes. And then in this case, so what is mu? So mu is just something like the 1/2, 1/2, negative 1/2, negative 1/2. I mean this. And of course, when the group becomes larger, or it's actually when the group is ramified, then it becomes more and more complicated. Okay. So now we are talking about the other map. From the special fibers of the Shimura variety goes to this B of G. And so this is a Cartwright-Rappaport conjectured. And then I proved recently is the following. The natural range of this map, delta k, is B of G mu. Now if you pick up any element, pick up any acceptable element, then this one is a Newton strata. And what is the basic Newton strata? So remember this one, so this is an identity, this is inequality. If you look at this inequality, there is a unique minimum element. Minimum element, I call it tau. Then this one, so this one is what I mean the basic locus. In most cases, the basic locus is just a super singular locus. But I do not know if this is always true. OK. So now we have this map, and we have the two stratifications of the spatial fibers of the Shimura variety. And of course, when one wants to think about this, a very fundamental question is that whether or not they are non-empty. Or if it is empty, then this not one can talk about. Well, so we have this axiom 1 to axiom 5 here. So we have this axiom 1 to 5. So this we actually guarantees the non-emptiness of both the Cartwright-Rappaport strata and also Newton strata in the natural range. OK, so this is actually based on these axioms. Now, in which cases we actually already know this. So, so these axioms, now we actually know these axioms in many cases are verified in many cases. In the Ziegler case, I mean SP, so this is already in the joint with Rappaport, and also in the unramified PEL, and also in the ramified odd unitary. So this is a joint work with Zhou. So he's a student of Kissin, and if I note correctly, he will be a member of the institute starting from the fall. And also, he verified for some Hodge types. So this is a work in progress in this case. That's in progress. So now we actually know at least these axioms hold in many of the interesting cases. Now from now on, we're going to assume that we have these axioms so that we don't have to worry about the non-emptiness. And then we're going to come back to this question. OK, so when trying to understand what I mean in the certain cases, the basic locus has a nice description. All right. That is a good question. Since I'm being recorded, I would like to say that at least for p not equal to 2. Well, Shields has working on the local models for p equal to 2. I'm not sure. I mean, this is the very new situation. I'm not sure. I'm not 100% sure if those axioms need some modification or just true as it is. OK. Well, so in the beginning of the talk, I said that I'm going to answer 3 questions. When, why, and what else. So now I'm first going to answer the third question, what else? OK, so under the axioms, the following are equivalent. First is that the basic locus admits, let's say, is a nice union of classical Deligne-Lussick varieties. Second, well, so this is about the basic locus. What happens to the other Newton strata?
Nice.
And, well, so naively, you can think about any scheme as the unions of the points. But this is not what we want. And in fact, we have another way to reformulate this. Just we say basic locus is in fact a union of another strata of the spatial fiber. So in the Iwahari case, then we can just use the Cartwrights. If this is in the hyperspatial case, then from the previous work, we know that we should use the Ekta-Ott stratification. For arbitrary parahoric, then we just use the interplate between the Cartwrights, Rappaport, and Ekta-Ott. Or maybe let me put it this way. I'll say this is a union of Ekta, Cartwrights, Ott, Rappaport strata. And So this is about the basic locus. For the non-basic Newton strata, for any non-basic Newton strata, I would say no. Any non-basic Newton strata stratum is a union of central leaves. So in general, if you have the Newton strata, then you can actually have this underlying reduced scheme, and then the fiber just the central leaves. So here this just says that the underlying reduced scheme is just the fundamental points. And third one, so I would say for any non-basic B inside this BG mu, if you think about the pairs mu and B, this is Hodge-Newton decomposable. So I'm going to explain what do I mean this later. But let me first finish this. And the fourth condition, in fact, we can make this very explicit as the conditions on this mu. Well, the case we consider just for arbitrary reductive group. For example, we can also consider about the non-quasi-split group. But for simplicity, I just write down the condition for the quasi-split group. For quasi-split group, the condition is that the mu plus sum will be less than or equal to 1 for all sigma orbit. C on the finite roots. So this is a question we start with, and also then finally we found that this one we're interested in is also equivalent to some other very nice properties on the Shimura varieties. Well, I should also point it out that although these first two conditions depend on k, but if you look at the third and fourth condition, there's no k. So in fact, this condition is independent of the parahoric subgroup, parahoric level structure you choose. In particular, this is independent of k. And well, the fourth condition, well, so now I have to mention the things that I'm not quite familiar with. So there's a conjecture of the Fag and Rappaport about the weakly admissible equal to admissible. I don't remember right now the precise definition, but they have the conjecture on that. And then this condition for the quasi, well, the only conjecture for the quasi-split case. And then this is exactly the condition they have there. So in some sense, this is still related to the geometry. And also, so this fourth condition is also very useful to answer another question. When does this happen? So now we have the second result, the classification. Because this is a purely group theoretical condition. And one can check this very easily case by case. So when does this happen? So we have the family. So the family it is either unitary or orthogonal. So it could be the fake unitary. Where I have put this just the case of the Harris-Tyler.
Sorry.
Yes.
Classification of what?
Of when this happens.
When which happens?
When this four condition happens.
When these four, I see.
G H of the Shimura variety for the condition 1, 2, 4. So, and then have the Dreamfield case. So Dreamfield case, we only have the basic locus. Basic locus is everything, and this is also true. And also, see, what do I have? We have this the U1n of Hermitian form. So this includes both the unramified and ramified. And we'll have the Hilbert-Brunner. And then we have this SO2M of quadratic form. So these are just those families. And also we have a few exceptional cases. So we have this is the U22, unramified and ramified. And we also have SP4. And also we have a few others.
So if you take SP6 or something, you see completely new varieties somehow occurring.
So what actually happens in general is that if you think about the underlying reducer schemes from any Newton strata, so in general, then what one gets is the Affan-Deligne-Lustig variety. And then the Affan-Deligne-Lustig variety, so there's a Deligne-Lustig reduction basically says that in each step, this can be written as a union of the two things. One is just A1 bundle over a smaller Affan-Deligne-Lustig. The other is just the A1 bundle with a zero section removed from another smaller Affan-Deligne-Lustig variety. And you just keep this going. Essentially, you get something finite. But I mean, this involves many steps, and in general, this is very complicated. So even for the SP6, one has to use the affine Deligne-Lucid variety. There's no way to decompose this as a classical Deligne-Lucid variety. And also, so these properties actually does not hold. For example, the non-basic locus is also much more complicated. This non-basic Newton strata is also more complicated because this has some reduced underlying reduced skin of positive dimension. I mean, I was saying this is actually kind of the mysterious that I mean, if the basic locus has a nice description, then also the non-basic locus has a nice description, and vice versa. Okay, so let me explain a little bit of this Hodge-Newton decomposable. So, what is a Hodge-Newton decomposable? So, roughly speaking, so let me draw the Newton polygon. So let's say we have this mu. So this is just the Newton polygon for mu. And okay, for mu and b. So b, we have this this gives another Newton polygon. I would say let me see if I can do this nicely. So this one is a new b. So roughly speaking, this is Hodge-Newton decomposable if the breakpoint, if some breakpoint of this new b is exactly on the Newton polygon for mu. So this has this breakpoint, and so this breakpoint, this will actually lead to a Levy subgroup. And why we actually call this the Hodge-Newton decomposable? Because this will lead to the decomposition. Okay, so the Hodge-Newton decomposition well, this is first studied by Katz for the F crystals. And then this has been studied by many people, the Cartwitz, Mann, Tovem, and also Chen, Kissin, and Feynman, and many others. So this is for, I mentioned the affine Deligne-Lucid varieties, and also the Rappaport-Zinc space with hyperspatial level structure. So what it says that if you look at the Rappaport-Zinc space for the hyperspatial level structure, then this is isomorphic to this Levy L, mu L, BL of this KL. So you can think about this large representing space for this whole group. Then this just isomorphic to this smaller group. And this is for the hyperspatial level structure. And now what we do is that we actually prove this for arbitrary paraholic. Paraholic level. We have this one. And that is quite interesting is that now we do not have a single piece. We have many pieces. Correspond to the sigma stable parabolic, which is conjugated to this one. Let's see, L prime, mu L prime, BL prime, KL prime. So we have many pieces involved, but still we have the nice decomposition. OK, so now I have 3 minutes. Let me briefly mention the outlines of the proof. OK. So outline of the proof. So we have this condition 3 and condition 4. So these 2 conditions, one can show easily that they are equivalent. So this is just some group-theoretic statement. We can show that these are equivalent. And also the 4th condition is about these inequalities. So one can see easily that this leads to the classification. The hardest part is to see how this actually relates to the first 2 conditions. So first, we're going to use the 3 and 4 to imply 2. And then we're going to use the 2 where it implies 1. And I think it's better to use a different color. And then 1 actually implies 4. So here, remember the 1 actually, so this is a statement which involves the paraholic level structure K. And in fact, so this last step is actually quite involved. And in fact, we have to do the case-by-case analysis for this. And well, so I'm not going to explain this technical part. But I can see briefly how we go from the 2 to 1. So the essential idea is to use the this stratification. And then plus the Lustick's so-called find the linguistic variety in the classical case. Well, so maybe I want to say more about how the 3 plus 4 implies 2. Let me see, I'll just do it here. So actually, how the 3 plus 4 imply these conditions on the non-basic locus? Well, first we know that this is actually everything is Hodge-Newton decomposable. So we use the Hodge-Newton decomposition.
So can you say a word about in this 2 implies 1, how you go from?
Oh, so from the 2 implies 1. So we know that the whole spatial fiber will have the stratification. So we have this Shimura variety K. So this is the disjoint unions of the Newton strata. And this is also disjoint unions of the, I have to use some finer stratification than the Clausewitz-Rappaport. And then 2, so if you look into the details of this condition 2 actually implies that for any non-basic Newton strata, it is the unions of the echo strata. And then this, because except those non-basic Newton strata, the only one left is a basic Newton strata. Then we know that basic Newton strata is the unions of the echo strata. Then this actually plus the loci find the linguistic variety and some other techniques. Then we know this is in fact this is the natural unions of the classical linguistic varieties. And so finally, how this 3 plus 4 implies 2. First, we use the Hodge-Newton decomposition. Well, this involves many levies, but nevertheless, then we know that. So we want to consider about this, the pairs mu L prime and this BL prime. So for the proper levy, and then we use this condition. Because the mu together with this is less than or equal to 1. Now, if you restrict this to the levy, so we have some common breakpoint. This common breakpoint, if you forget about this will actually contribute to this term. If you only look at the corresponding part for this levy, and then we do the similar computations for the fundamental weight of this levy, it becomes less than 1. Because of the breakpoint makes some contribution to that summation. And now, when does this condition happens? So this condition happens exactly in the Hobbes-Tyler case. And in the Hobbes-Tyler case, we know this is dimension 0. So this is dimension 0, and this is dimension 0. OK, we'll stop here. Thank you.